So we went over one complete example about how the variance value may actually change as we do state transitions. Either the state transition can be by the old events, or it can be by the new events. Let's recall this diagram over here, right? It's really important for us to connect to the current part of the lecture. If you look at the trend over here for the variance value, if the transitions are being made by the old events which already exist in the abstract model, in that case, it's going to increase the value for the variance so that new events can actually occur. And for every occurrence of the new event, it's going to decrease the value for the variance by at least 1 each time. So it's going to be strictly decreasing. And until we actually reach the point where the variance value becomes 0, in that case, we actually just need more occurrences for the old events in order that we actually raise the level up so we can down the level again by the new events, right? That's kind of the trend we learn about. So 2 observations. Number 1, the value for the variance should always be either 0 or above. Number 2, whenever you try to take the actions for some new events, in that case, you should strictly decrease the value for the variance. You cannot keep the value the same. You must strictly decrease it. In that case, we will be able to bound the number of occurrences for the new events by some finite number. So that's exactly the purpose for the variance, right? Let's now move on. So what we want to talk about now is how to really formulate this idea about the convergence for the events. So there are 2 parts we want to talk about, right? So there are 2 parts, as you can see over here. Right, let me just go over slides very quickly just to show you about the proof obligation, and we're going to do some exercise together, and there will be some remaining exercises for you as well. Right, so we got 2 parts. The first part is about observation number 1. The variance value should really stay non-negative, either 0 or above, like a natural number. That's the first one, right? You can see the goal that we are trying to prove over here is the variance expression over here is simply a natural number, meaning that it's larger than or equal to 0, right? There is some comments over here which I'll talk about a little bit later. Okay, I'll get there. I'll try to visualize that as well, just in a moment. But the bullet points over here really try to generalize about the observations that we made from the earlier part for the example. Right, and the second part for the convergence proof is about the new event occurrence strictly decreases for the variance, right? The value should really be strictly decreasing, right? So the way to really formulate it, that will be something I want to do some example together with you. You want to compare 2 versions of the variance over here. The first version over here is in the pre-states of the W. And the second version over here is a post-state value for the variance. And you want to make sure the post-state value over here is strictly less than the pre-state value. So that's why we are decreasing the value for the variance, right? I'll try to make some, draw some diagram to visualize exactly what these 2 formulations are really corresponding to our 2 observations from the example, and then we're gonna do the exercise quickly, right? And the bullet points you can definitely go over them. They are simply just consistent with our observation from the example, right? Let's now talk about these 2 over here. Okay, you will see that the hypotheses are simply just the same as what we did earlier. You can see this part here is about axiom, abstract invariance, concrete invariance, and the concrete guards for the events. Right? And by the way, so for convergence, it's only specific to the new events. So how many proof obligation, how many sequence should we generate for each one of them? It depends on how many new events you have. So in this case, we're only going to do it for ILN for both categories of the convergence proof. And the remaining one for IL out, that'll be up to you. All right? So let me just make a quick note over here. Convergence is only applicable to new events, not for the old events. So that's why we don't have to prove the convergence for ML out and ML in, because they already exist in the abstract model, i.e. they have their abstract counterpart, but not for the new events. So for the convergence proof, only applicable to new events. To the new events. All right, and you can see the hypothesis is simply the same, AIJH, right? So for this part here, I'm just gonna copy and paste from before. I'll do that in a moment. And for the first one over here, if you take a look, for the first one, you can see the first one here is simply, oh, actually, you know what? Let me just highlight. That might be just easier. So we say that the expression V for the variance is actually a natural number. In this case, the v is really 2 times a plus b. And what can v refer to? It can refer to some constant, which is not the case for this one. That's okay. It can also refer to some concrete variables, which will be a and b. Right? So this one is rather easy. So what this one is really asserting is really trying to say that the value of v does have some lower bound. It should be larger than or equal to 0. That's the first one. That's the first one we are trying to prove. So this is really to say the expression v for the variance, which may refer to constant or concrete variables, should be always a natural number. Or alternatively, you can think about larger than or equal to 0. Right? That's the first proof obligation. What about the second one? The second one here is not too bad. It's also consistent with our observation from before over here. Right? As I mentioned before, it's really important for you to see the following. This part over here is the W in the pre-states before the transition of the new events. So this will be the pre-states. You can think about the pre-state evaluation for the variance should be strictly larger than the post-states evaluation for the variance expression, because over here, if you recall from before, this f over here is the formal components for the effects. So this is the effects of the concrete events. In this case, only just the new events. Only those events are applicable, right? And that is, this part over here is really about the post states of the variable. Right? How do we visualize this? So once I visualize these two expressions on the graph, everything will make sense. Let's see how we can do it. Okay? So you can think about, we have some pre-state evaluation over here, right? So this will be the v of c and the pre-state value for w, right? And then we're going to let the new event take place, takes its transition, right? So let's say this is specific to new events. It could be IL in, it could be IL out. Let me say EVT. And its guarantee is going to strictly decrease the value for the variance. So this will be the occurrence of certain events, like what we did earlier in the example. And this one here is going to decrease its value to the post states. So this will be the post state value over here. And what will be the post value? It's still going to be the same formula, like a 2 times a plus b over here, but the same constant, which doesn't change. But this part here should be w prime. And more precisely, the w prime over here should be replaced by the effects of the new events, which will be f of c w. Alright, hopefully that really makes sense to you. And this part over here is really about what we are formulating as the second proof obligation, right? So this is the second part. The first part is really about the variant value has a lower bound, larger than or equal to 0. And the second part over here is really about every time if the variant value has to change by the new events, it must be strictly decreasing. So that's why we got less than, we don't really have less than or equal to, right? Hopefully that's clear to you about how the formula should look like. And of course, if I simply swap the order of these two, in that case, it will be wrong. So you really make sure you want to make sure you really understand exactly what's going on over here. Let's now try to do some exercise about formulating this proof obligation as sequence. Let me now focus on IL in, the new events, and exercise will be for you to do IL out. All right. And the hypothesis over here, AIH, is very standard that we did also for other proof obligation. To save our time, I'm just going to draw that in 1 second. Done. Over here, right? This part here is really about axiom, abstract invariance, and also concrete invariance over here. What's really missing is about the concrete guard for ILN. What's really the concrete guard over there? Let's look it up very quickly. So for ILN, you can see the concrete guard is a larger than 0 over here, right? Let's go back. So that should be a larger than 0. So these are all the hypotheses. And then how do we actually do the goal for the sequence? So in tails over here, what about the variance over here? So this will be just the variant expression, which will be 2 times a plus b. So this will be 2 times a plus b is actually a natural number, right? This would be a very simple proof you can do, but I would suggest you also try to do it to see what kind of an inference rule can you really use. But I can tell you, you cannot really apply the simple arithmetic rule directly. You have to do a little bit of pre-processing before you can conclude, right? To prove it, it will be your exercise. What about the other proof obligation for the strictly decreasing proof obligation? Well, the same hypothesis, which I'm going to draw again in 1 second. Done. And then the same guard, because we're talking about the same events, ln. So that'll be a larger than 0, the same. And then we're going to say entails. And in this case, we got to be careful, right? So let me just try to do the following. This is going to be some final answer we want to put in, right? And I'm going to work out exactly what it should be together with you, right? You can think about it's going to be V of C W prime, right? The post-state value. What should be the post-state value in this case over here, right? You can see for ILN over here for this particular event. Let's now recall. I didn't have space to really put in the event, but let's take a look. For ILN, it's going to decrement A, increment B, right? Just remember that. Decrement A, increment B. So it's going to 2 times A prime plus B, right? And remember, A is going to be decremented. So that means 2 times A minus 1 plus B, right? Increment B, beg your pardon. Decrement A and increment B, right? It's going to be B plus 1, right? So far so good, right? You can see that one there. Let's see this. Think about this part over here, and this part over here is exactly the post-states effects, the action effects for that ILN events, right? And of course, I forgot to put prime over here. So what we're doing is we are substituting A prime by A minus 1. We are substituting B prime by B plus 1. We did similar exercises earlier as well, right? I assume you're okay. Right, so this is the final expression, only this part over here. That should be strictly less than the pre-state evaluation for the variance. So that means it should be strictly less than the pre-state evaluation for, let me just write it down over here, V and then CW, which is exactly equal to 2 times A plus B. 2 times A plus B over here. Just got enough space. So that will be exactly over here. This expression here is strictly less than this expression here. Let me write it down. So final answer should be 2 times A minus 1 plus B plus 1. Strictly less than 2 times A plus B. So that'll be the final answer. All right. And it will be also your exercise to actually prove this one. That should be also rather easy to prove, right? I think for usually to really prove these two proof obligation related to convergence, it should not be too tricky to really conduct. I think deadlock freedom might be the more tricky one to conduct, which we will talk about a little bit later. All right, so make sure you actually complete these proofs, and then you want to formulate the other ones proof obligation by replacing this by IL out, and also IL out, and also prove them as well. That will be your exercise. Let's now go back to the slides. Right, so all these have been explained already. You can look at the bullet points. And then that's the first proof obligation we just talked about. How many there should be? It depends on how many new events we have. 2 in our case. IL in, IL out. Right, so that's the proof obligation. You can double check, right? And also, we got the second one over here. You can also double check the answer. And don't forget about the exercises. So we already formulated the proof obligation over here as a sequence. Make sure you prove it. And also for the other one about IL out, the new events, you want to make sure you also formulate it and prove it. I'll leave the exercises to you. The next exercise, which I highly recommend you actually attempt, is to really think about some alternative variance over here. Rather than 2 times A plus B, what if the variance is actually A plus B? How should the proof obligation and sequence be changed accordingly using this alternative variance? Can you still discharge those sequence? Can you or can you not? If you can, that means the variance that we proposing over here is actually appropriate. Otherwise, it is not appropriate. But either why or why not, you definitely want to justify your answer. Right? So that's something I would highly recommend you do, and try to practice about formulating the sequence for convergence proof, the two parts, and also try to see if you can prove them. And don't forget, you can also use the more intuitive approach to really try to simulate the transitions, like how we did it in the earlier part for the lecture. Right? Try both, and then before you move on, and we're gonna the next part we're gonna talk about relative deadlock freedom.